right. Good afternoon, everyone, and thank you guys for being here. Welcome to our August 2025 installment of ENERCALC Office Hours. If you've been with us before, you know the drill. We got just a few housekeeping items to get through before we start the program today. If you're joining us for the first time today, there's some interesting information in the front matter just for you guys to be aware of. So before we get going, I just want to start with a quick sound check. If you direct your attention to the bottom menu of your Zoom window, either in your browser or your desktop app, you'll be able to see the chat tool. We also have the reaction emoji tools in the Zoom window. So if you're able to hear me just fine right now, go ahead and give us a thumbs up, give us an okay in the chat, give us some sort of a reaction emoji, some applause, what have you. That's perfect. Thank you guys. Before we get on to the rest of our front matter and introductory stuff, I also want to do a sound check and visual check for our primary speaker as well. So Mac is going to go ahead and share his screen at this time. And as soon as he does that, then once again, if you can hear Mac's voice and see his screen, go ahead and give us a thumbs up, give us an okay, your reaction of choice. Go ahead, Mac.
Hello, everyone, and welcome to Office Hours.
Perfect. All right, now that we have our tech checks out of the way, we are going to go ahead and disable the chat so that we can move on to our introductions. If you do have questions for the team today, we have the Q&A, the Q&A dialogue for that. So as far as introductions, my name is Seth Roseworm. I'm a senior structural engineer and software developer here at ENERCALC, and our presenter for monthly ENERCALC Office Hours program is Mac Helterhoney. Many of you know Mac by now. A lot of you know him professionally through his engineering company that he operates, and then through ENERCALC as well. So Mac is a senior structural engineer here at ENERCALC, and he splits his time between providing technical training for ENERCALC customers, working with the ENERCALC engineering team on the specs and behavior, technical behavior of our software, and then also helping maintain a presence for ENERCALC at national events and regional events throughout the industry. Mac is also the founder and managing principal of Elta Design Group, which is a specialty structural engineering firm based in Oklahoma City. And he's been an ENERCALC user for over a decade at this point, so he has a lot of great insight about the needs of our customers. So for anybody who's new here this month, the Office Hours program is meant to provide simple, direct communication between us and our users, and we do that through several avenues. We showcase new features to show you guys what's been updated in ENERCALC, what's the latest, greatest behavior of the software. We show optimized design workflows through deep dive walkthroughs in specific modules. We answer questions submitted in writing. We also answer live Q&A questions that are submitted during each session. And if there's ever a question that's too involved or it's going to require deeper digging and research, that'll be a better fit for our support team. And we'll be reminding you later on today how you can reach the support team so that they can investigate your concerns, look under the hood in the program, and get deeper answers for your questions. As a minor point of order, you will notice everybody's microphones are muted just to make sure we don't get any echo or feedback while Mac is presenting today. As I mentioned, we do have open Q&A at the end of our session. Every monthly office hours, we do that. So if you want to submit a question for today's Q&A, just use the Q&A dialog in the dashboard of your Zoom window, and we'll answer those questions at the end of the session as we go through them. If you ever experience audio problems at any point during the session, you can simply refresh your browser or jump out and rejoin the session, as well as using the native audio controls in your Zoom window. If you ever want to rewatch today's program or any of our previous Office Hours programs, you can access all of those from the Office Hours playlist on ENERCALC's YouTube channel, which you can also access from our website on the Office Hours page. And with that, I will go ahead and hand it over to Mac to get going on our program for today.
Thank you, Seth, for the introduction of the housekeeping items, and again, welcome everyone to another great session of the Office Hours program. My name is Mac Helterhoney, and I'm excited to be presenting to you today the CMU, or the Masonry Slender Wall module, from the ENERCALC's library of diverse and extensive modules. So I would like to start our session today with a brief overview of the overall agenda. Have a quick announcement for PDHs, and then ENERCALC latest build, what's new in ENERCALC, and then we'll dive right into the CMU Slender Wall module with an example. And then finally, we'll have registration for future office hours. And we're going to talk to you a little bit about future events. And of course, last but not least is the live Q&A portion of our presentation. So if you have any questions, you can input those, or you feel free to drop your questions in the Q&A form throughout the presentation. So, beginning with the session that was held in May, we started offering a zero point 0.5 PDH to the attendees to represent the guaranteed technical portion of the presentation. The name that we use in the certificate is the same name that you used to join this Zoom session. So please make sure that you enter the name that you want printed on your certificate. And of course, if it's ever, the wrong name, or you have any issues with it, you can always email us or email me at the office hours email, and we can rectify it for you. And last thing is that certificates will be emailed separately, so you'll have a separate email that typically comes out about 10 days after the live session. And again, if 10 days pass and you don't get your certificate, please let us know, and we'll be more than happy to email you a certificate. So first, I'd like to encourage everyone to check your software, make sure that you are on your latest and greatest build of ENERCALC. And that's a very, very simple process. You just open your ENERCALC and look at the very top, and you will see here where it says build, and that is the number. So we do have, we release updates monthly for ENERCALC, where we update a lot of features, fix bugs, do all kinds of stuff there. So we want to make sure that you are taking advantage of all of this work. A lot of times people might have some issues, and those issues get reported to us, and we know them and we fix them. But if you're stuck on not updating your ENERCALC, then your issues might not be, or you would still have problems. But if you just update, you'll at least have the latest and greatest and be up to date. At the way to update ENERCALC is just you would have this icon right here at the top upper ribbon bar, and if you just click on update, that will pop up this window right here. And if you click on this button, which is click to launch the For Our Users page, you will be able to go to the website, and then you click right here to download the updater. And once that file is downloaded, you can of course launch it, and you will be running the latest and greatest. So it's a pretty straightforward process. And of course, if you'd like the program to automatically check for updates at program startup, make sure you check this option right here. And currently the build that we're on is 2025-0731, and this was released in July 31st, which was about 2 weeks ago. A quick note here for our users who are stuck on this build right here, 2023-830, 2024 228. So if your build is in between these two numbers, or within this range right here, then the feature to notify you of the availability of new updates does not function properly. And to fix this, you will have to update the program manually just one time. So this way, this issue gets fixed, and you will be able to be notified in the future of all new updates. Again, the current build is 2025-0731, so make sure you update to the latest and greatest. If you prefer to be notified of the latest ENERCALC updates by email, you can always scan this QR code or go to enercalc.com/update-emails. And that will get you this form right here. Once you sign up, then you'll be receiving those updates directly into your email, so you know what the new updates are to the software. So if you haven't had a chance to look into ENERCALC recently or see all of the new stuff, I just want to highlight a few of the features quickly so we can jump into our main portion of the presentation today. The first part is IBC 24 and decoupling of the IBC and ASCE editions. So to select your IBC edition to be used for your project, you can click on the building code and loads combination button at the top right here. This will open this menu for you to select the proper IBC version that you want to use. So as of March, ENERCALC started supporting IBC 2024, and of course, all of the referenced designed standards that are referenced in the IBC 2024, such as your AISC the 2022, NDS 24, and of course your TMS 40222. However, we decoupled the ASCE edition from being hard tied to the IBC edition. So everything here is hard tied. You can't mix and match these. But we went ahead and decoupled the ASCE edition. So for example, you can use 2018 IBC with 2022 ASCE 7. And the reason for this is because a lot of jurisdictions started mixing and matching the ASC with the IBC. So we wanted to give, of course, our users the flexibility they need to produce robust calculation packages and minimize the need for PDF markups or manual post-processing of the calculation package. It is worth noting that changing the governing code or the ASC edition from this menu, it's only going to change for this project that you're working on only. It's not going to be the default setting for future projects. If you need to change ENERCALC to make it use IBC 2024 or a specific version of the ASCE or whatever combination you want, if that's what you want to be using for all of your future projects, then you go all the way to the top left corner, click on settings, and then click on default governing code from the drop-down menu. Then you will get this window. You can choose the IBC edition you want with the ASCE edition you want, ASCE 7 edition you want, and then you click select. Once you do this, all of your future calculations will have this as the default code combination. Next is the new tabs that house the ASCE 722 loads and forces modules. So we have a tab right here for seismic loads, another tab right here for wind loads, and another tab here for other loads, such as live load reduction or snow loads or other things that we can add there. So this is a little bit different from the old way of doing things. So in this, if you're on ASCE 722, a user can create a calculation for whichever one of these they want, and they can create as many as they want. Previously, the user only have one calculation per load and force module. So you can't create multiple of these. You can't create multiple snow load calculations. You can only have one. So it's important to note that these tabs, these three new tabs, will only show up if you have selected ASCE 722. If you selected ASCE 716 or older, then ENERCALC will revert back to the older modules in the older menu. So to give you an idea, if you're using ASCE, or to remind you, if you're using ASCE 716 or older, then all loads and forces modules are preloaded and can be accessed, this way, where we have folders for them right here. And of course, you cannot make copies of this. This is just a one calculation per project. But of course, if you are on ASCE 722, then these will pop up right here for you as tabs. Next is native load linking within ENERCALC, and this has been an exciting feature with rapid development. For those who don't know anything about it, load linking is an ENERCALC native feature that gives the user the ability to automatically link reactions from one calculation to another, and the ability to change something in one member and have the effects of that change trickle down to all of the supporting members, all of the downstream members. Load linking is currently available for steel beams, wood beams, steel columns, wood columns, and of course with more integration coming in the future. If you would like to learn more about load linking, I created a playlist of short videos on YouTube right here that walks you through how to use load linking in a step-by-step fashion, and it kind of explains a lot of tips and tricks. And you can, yeah, this will allow you to leverage this powerful tool very quickly. But we also added to this playlist, we recently added a full example, a full practical example of how to use load linking in real life design applications to transfer, reactions from beams to columns. And of course, the example is made to cover various materials. So you have, from wood beam to a steel column and steel beam to steel column and all kinds of fun stuff there. So again, overall load linking is a powerful tool that allows the engineers to create a well-connected chain of calculations while minimizing the risk of transcription errors. And we've had a lot of great feedback so far from our users saying that this has been a huge time saving for them. So if you have not tried this, I would totally encourage you to try it and give us your feedback as we continue to grow this product. Another update is the ability to export tabular detailed results from ENERCALC to a CSV file. This is useful to many engineers who want to post-process some of the results outside of ENERCALC. So all you need to do is just find the result that you're looking for, find the table you're looking for. For example, I'm looking at the ASD shears and moments. All I have to do is just right-click and save to CSV, and that will download directly into your computer. You can do this and download results or export results to CSV file. You can do this for pretty much all of our modules: columns, beams, slender walls, shear walls, foundations, and all of our analysis modules. So you can do this for practically everything we offer in ENERCALC. And of course, by popular demand, we made an important update to the general footing module, and that is the ability or the option to specify top reinforcement in the footing for those cases where the footing experiences tension at the top rather than the typical case where the tension is at the bottom. So you can specify the rebar size and quantity separately for each direction, top and bottom. So you get this covered, the X direction and the Z direction for the top, and of course from before you have the X direction and the Z direction for the bottom. Also, here this is a sample result display here. It shows you that we added kind of extra helpful notes that tells you this is the top tension, and the direction, just so you understand what you're looking at here, to just make things a little bit easier to navigate as a user. Moving on, we have, of course, ENERCALC for Revit, and I want to highlight that because ENERCALC for Revit is it's a plugin that allows you to design structural members fully within the Revit environment without having to export any information to another calculation software. You're not exporting analytical models. You're not even maintaining an analytical model for that matter. You're not doing anything. Everything is done automatically and completely within Revit, and it's just simple point and click. You have guided prompts. As soon as you click on something, it tells you, hey, is this the support? You say yes. What do you want to use for the slenderness? You want to use a K of 1, a K of 8, or a custom, or so you get this point and click guided prompts. It's almost like another engineer asking you for this input information. Once you suggest this, it automatically takes you to ENERCALC and allows you to do the design in a fraction of the time that it would take you otherwise. And of course, you have powerful graphical interface in here, and as well as highlighting statuses. If it's green, then it's good. If it's red, it's bad. So, you have all of this, which allows you to review the models and the calculations very easily. If somebody else did the work and you're just checking it, and making sure it's done right. And of course, we have a full gravity path because you have beams, you have columns, you have all the way to the foundations at the bottom. And it does composite beams as well. So we keep on adding more and more to it. And with every new update to ENERCALC, we send release notes to outline what changed and what got updated. So if you want to subscribe, you can always just click on the update button, and then you click on here, and this will tell you exactly what changed. Every time we release a new update, it'll tell you exactly what changed. And the email is very simple. It's going to look something like this. It gives you the highlight of the top things that changed. So for example, hey, we added top reinforcement in the general footing. We added flexural details and soldier pile retaining wall module. So it gives you just an idea of what happened. And then of course, at least the major highlights. And then you can click on this link that's in the email, and it will take you to all of the changes that we did, especially if you're trying to follow a particular change. So moving on, the focus of today's presentation is the design of masonry slender walls for gravity loads as well as out of plane loads. Here's a quick overview of the capabilities and features of the Masonry Slender Wall module. It performs analysis and design to check the flexural capacity of the wall. ENERCALC considers P little delta effects from the gravity loads. You can do 1- and 2-story wall design with parapets. User can apply lateral loads, concentrated loads, uniformly distributed gravity loads, lateral loads. There's all kinds of loads that you can apply in loads combinations between, again, concentrated and lateral and distributed. Implements TMS design provisions and limitations for walls with height to thickness ratio exceeding 30. So practically you can design anything within of course, the applicability limitations noted in the TMS code. And dynamic 2 and 3D sketches for visual confirmation of the overall construction. To start a new masonry slender wall calculation, we follow the same process. You click on the Add button, then you navigate to the Walls tab, and then, of course, Masonry Slender Wall, which is this one right here. You click on that, and you are in business. As always, we work our way through the tabs from left to right. This is just the general theme, and we'll start with the General tab. So we're going to give the calculation a name. It's going to be a very generic name, exterior CMU wall, nothing fancy there. And then we're ready to move on to the first part of this, of the input, which is the material properties. So the first thing we need to input here is the F prime M, which is the masonry compressive strength. And I'm going to be using 2 KSI, which is 2000 PSI. Next, Fy of the steel reinforcement, the rebar, we will be using grade 60 steel, so Fy of 60 KSI. And then I want to note here for everyone to keep in mind that this module designs CMU using the strength design method, not ASD. So we will be using the full 60 KSI, not the traditionally reduced value of 32 KSI that many engineers, and myself included, are used to for CMU ASD design. This is kind of just the direction that everybody's going, or at least the code is going, and it seems like it's going to be a lot more aligned with the ACI, so might as well jump right into the strength design method. Next, we have to pick a value for FR, which is the modulus of rupture. This is important, especially for cracked moment calculation. If you click on the FR button, this one right here, you will get a quick reference window that ENERCALC kind of includes there for you. And this has the same information in that reference window as the information that you see here on the left from the TMS table 9192, which is the modulus of rupture values. In our case, the current construction is partially grouted CMU with regular Portland cement mortar type M or S. So that puts us right here. So we are partially grouted and we're using just regular mortar, not air trained and M and S value. So we're looking here and it's, we're using hollow units. And what I want to allude to here is the options that we have, you have ungrouted or fully grouted. You don't have partially grouted. However, they do allow you for partially grouted masonry. You're allowed to interpolate between these two values. However, for this example, I'm just going to be a little conservative and I'm going to use 84, which is the ungrouted. And this way I can just kind of run my numbers with that and I don't have to do any extra work. But this is the designer or the user's responsibility to pick the proper FR that represents their construction assembly or their wall assembly. So this is a completely user input and you can put whatever you want. So for us here, for this example, I'm using 84, which is this value right here. So the next item we have to specify is EM. This is the modulus of elasticity of masonry in compression. And ENERCALC allows you to use whatever multiplier you want. So for CMU, EM equals F prime M multiplied by 900. This is a user input number right here, but we get this from the TMS. So that is 900. Lastly, we need to provide a little bit more information regarding the wall itself. So we plan on using 140 PCF grout density and just normal weight blocks, but you can use whatever you would like again. So moving on right here, now that we finished with the material property, now let's get into the wall itself a little bit. The first thing is we need to figure out the wall size. And in my case here, this is the wall is 8-inch CMU. So you can just click on it right here and it automatically provides you here the actual thickness, which is 7.625. So ENERCALC can design walls with a single bar centered into the cell or with 2 layers of reinforcement per cell. In our example, we will be using a single bar centered in cell, but and that's why here the rebar distance, the D distance, it's automatically 7.625 divided by 2, and it knows that. So once you pick this option, you're good to go. If the wall is solid grouted, then you can check this second box right here. And this means that every cell will be filled with grout, even if it doesn't have rebar. This will increase, of course, the wall weight. This is the wall that we're designing is not part of a storm shelter, is not part of any fancy assembly. This is just a regular wall, so there is no need for us to have it fully grouted. So I unchecked this box. ENERCALC here calculated the weight of the wall to be 51 PSF. Now, it is worth noting that if we uncheck the option for the center of the rebar on the wall thickness, the user will be prompted to enter their own number for what that D distance is. Because in the beginning, if it was just in the center, it could auto-calculate it, but now you have to. It's kind of asking you, what do you want to do? You want to put them side by side and it's still centered? You want to move them around? So this becomes part of your of the engineer's responsibility to determine what that D is, and of course make sure that that's properly detailed on their drawings. And additionally, if you click on the solid grouted wall option, you can see that ENERCALC auto-calculated the weight of the wall, and now the weight of the wall is 86 PSF instead of the 51. Again, our example is not going to use solid grouted wall, but it's worth just showing you the difference. Lastly, let me see here. Yeah, and then there's this part right here that is the rebar size, and that's kind of the last piece of the puzzle, which for this example I'm using single number 5 bar, and I am putting it at 32 inches on center. And you can play with the spacing as you need, whenever you work through the example. If if the wall is not strong enough or the wall is failing, then of course you can change the bar size, you can change the bar spacing until you converge on a proper solution. Lastly here, we need to adjust the analysis settings to our liking. First, you will have the option to calculate the I effective, the moment of inertia, based on mu at the element, or based on the I cracked full height. In this example, I'm using I cracked full height, which is more conservative a little bit, but I think it's more appropriate for my application. If you have a temperature differential across the thickness of your wall, you can check this option right here. And what happens here is that if a temperature differential exists, then the resulting deflection from this temperature differential will be added to the calculated deflection of the wall. So the way this works, this is going to be additive. We're not going to be you're not going to be looking and trying to see if this helps you with deflection, or if it's good, or if it's bad, if it's plus deflection or minus deflection. This will, or at least the way that ENERCALC handles it, it will be always added to the amount of deflection that we calculate just from the lateral load and the P delta effects. So then the next piece right here we have is the minimum vertical steel. That's a ratio. So we're using 0.002 times BD. And then we have the minimum allowed span, deflection ratio. Typically, and this is something that the user will have to specify, obviously, but typically walls are designed for L over 150. This is a common number that many engineers use. I see it in concrete tilt-up walls. The ACI mentions the L over 150 limit for the slender wall alternative method design noted in the ACI. But for CMU, the TMS calls out for 0.007 multiplied by h, the height of the wall, which comes out to be kind of L over 143. So it's close enough, but this is the proper way of follow, or at least not the proper way, but the TMS way of specifying deflections at mid height. So that can be used there for us again, because 0.007 h, this comes out to be L over 143. So for now, I'm just leaving the L over 150, but this is of course the user responsibility to determine the deflection limit. Lastly here, the number of wall segments used for analysis can be left as is. 35 segments is typically more than enough. However, the user can adjust this in case the results need to be refined. If you use a small number here for the analysis, that might give you a little bit of different results, or less accurate results. But once you reach to a certain point, 30, 40, whatever it is for your wall, adding more segments doesn't really refine the results anymore, because it just kind of converges. The difference will be a 0.0001 or something like that, something that's not it's not needed anymore. Not that level of accuracy anyways. Moving on to the next tab, which is the dimensions tab. You can pick if this is a single story versus a two-story wall. Our example is a single story span, so we just click on this one right here. But if you have two, then you click on this, and our wall also does not have any parapet. If you did, or if it did, this would be the place to input, the parapet if you have 3-4 feet, whatever parapet you have. The total span is 16 feet, and it's considered to be pinned at the top and pinned at the bottom. The height to thickness ratio of this wall is calculated here for your convenience, which is 24:1. ENERCALC follows the TMS design provisions that allow you to design walls of all heights, pretty much. So the TMS has limitations for treating these walls or limitations for treating walls that meet a height to thickness ratio of 30:1 or less. And there is a different limitation for heights that exceed the 30:1 ratio. So in our case, we're good right here with a ratio of 24:1, which is less than 30:1. Either way, ENERCALC performs the proper calculation based on either limitation, based on whatever you fall within that height to thickness ratio delineation line of 30. It performs, the proper calculations and checks to ensure that your wall is in compliance with TMS provisions and limitations. So we're good here since we're less than 30. So we're going to be using the traditional, straightforward method here. And lastly, under this tab, we have the design width of the wall portion, aka the strip width, which is right here. We're using 12 inches for the design, so I'm just going to keep that as is. So all of my work, all of my design is based on a 12-inch strip. Moving on to the next tab, which is the loads tab. ENERCALC allows you to apply vertical and lateral loads. And we will start with this vertical load subtab right here. There are two types under this subtab. You can apply uniform loads at the top of the wall, and these loads can have eccentricity. So this is similar to what we would call a ledger load. This is a load that is framing to the side of the wall, for example, maybe with an edge angle or maybe with a nailer or something. So this is kind of ledger top of loading. So we want to apply 30 PLF live and roof live and 30 PLF dead. And ENERCALC takes everything in kips per foot, so that'll be 0.3, and I apologize, not 30, but 300 PLF for dead and 300 PLF for roof live. And they are applied at 6-inch eccentricity, and the eccentricity here is measured from the center of the wall. The eccentricity is measured from the center of the wall. So the second part right here, this is for concentric loads. So this is for concentric or concentrically applied uniform load. So if your load doesn't have eccentricity and applies directly on top of the wall, or maybe you have a pocket that you created inside the masonry, then you can apply that load right here if it is directly concentric on top of the wall or on top of on top of the cell. So with that being said, you get the same effect if you turn this 6 into a 0. If you turn it into a 0, then it is also, this line becomes concentric because there's no eccentricity there. So that's part number one of, or this is the first portion of the loading here. The user can also input point loads, and those point loads can be placed anywhere on top of the wall. So you can apply here a load at maybe eccentricity of 5 inches, and you put dead load, roof live, or whatever, and maybe you want to apply this at the middle of the wall. So instead of applying it at 16 feet, our wall is 16 feet, so this is the distance from the base. If you say 16 feet, then this load will be applied directly at the very top of the wall. But if this load comes, let's say, maybe from a lower load or a lower joist or maybe some sort of additional canopy load or something, this can be applied at maybe 10 feet above the wall or so forth. So you have the ability to do this right here if it's a concentrated load. And it's important for you to know that this concentrated load is actually distributed over the strip width. This is something that's very critical for you to know. So if your strip width is 12 inches and you applied a 3-kip load, just know that this load is kind of spread at that strip width that you've initially selected. And the strip width we selected for this project or for this design is 12 inches, but if you selected a 48-inch or something bigger, just be aware that your load is getting, your concentrated load is getting spread over the width of the strip. The next sub-tab is the lateral loads. So first we want to input the full area wind load in PSF. And our example is subject to 28 PSF full area wind load. This is wind load that's applied just at the whole whole wall. And again, this is 1.0 wind because this is strength design. So this is unreduced, unfactored, straight up ultimate wind pressure. And the second part to this, that is where we enter the seismic load due to the wall weight. So we have 3 options for how we can enter the seismic load due to the wall weight. First of all, you can just enter lateral loads. This is straight up. You just click on this and you put your own number, 10 PSF, 12 PSF, whatever that number is, and you put it right here, and that will be used. That's the easiest way. Well, all methods are easy, but that's one way. The other way is you enter the wall weight factor. So this factor will be multiplied by the weight of the wall to determine the wall weight seismic load, which is FP pretty much. So ENERCALC auto-calculates the weight of the wall for you. And this is shown under the general tab. If you remember, we saw this earlier under the general tab. The weight of the wall is 51 PSF. And whatever factor you applied here to the wall, for example, a factor of 0.19, it gets multiplied right here, 0.19 times 51, it's 9.69. That's what it is, and that's what gets used. The third option is you can enter SDS multiplied by the importance factor, and you just input this number right here. The SDS value you input must already be multiplied by the importance factor, and in this case, we are inputting 0.5. So ENERCALC will calculate the wall seismic load based on this formula that's shown right here, which is 0.4 multiplied by I multiplied by SDS multiplied by the wall weight. And this is an important note. ENERCALC is telling you that you need to check this separately. You need to make sure that the 0.4 multiplied by I multiplied by SDS is more than 0.1, because if it's less than that, ENERCALC is not going to flag it for you, and then you're not following ASC 7 anymore. So this has to be checked independently by the user, because if whatever number you put here, even if it does not satisfy this check, ENERCALC will not flag it. This is a check that you perform independently. So in our case, this is not going to be an issue. This check is satisfied. So 0.4 multiplied by 0.5 multiplied by 51 gives you 10.2. Either way, all of these are, seismic loads that are less than the wind loads anyway, so they won't control. But if they did, this would be important for you to worry about. Moving on here, now that we applied our wind and seismic lateral loads, we are ready to move to the bottom of the page because of that tab. So we just applied this load. Now that this is where we have a great level of flexibility in applying loads. You can apply concentrated lateral loads at specific heights above the base. You can apply up to 2 different point load sets, as you can see right here. And And again, all of this will be applied to the full strip width. Next, which is this side right here, you can apply additional distributed loads, again, up to 2 different sets. And the uniform lateral load can be full height and it can be partial uniform load that maybe occurs within the bottom half, or maybe from, the wall is 10 feet. You can specify that the load starts at 2 feet and it goes up to, maybe 10 feet above the base or whatever. So all of the work here is done from the reference, which is the reference point, which is the base, but your distributed load doesn't have to be fully uniform or full height. It can be partial uniform load. And between these, definitely this covers a lot of grounds as far as various loading conditions. And lastly, we have the load combinations tab. I'm using IBC 2024 combinations. User can control the combination for strength or reaction or deflection independently, as you can do in many of our other modules. ENERCALC uses a strength design method for CMU design, so the combinations, of course, are all LRFD, and that's something for you to keep in mind, just because many people, again, myself included, are very used to designing masonry in ASD for the longest time. So it's always important to remind yourself that you're not working in the ASD domain. So with that, we have concluded all the required input and we're ready to check the results. So I want to briefly go over what you can see here in terms of results. You have the calculations tab, you go to the summary, you can see the maximum bending stress ratio. You can see, and this is of course passing with flying colors at 0.56. And then the deflection limit here, L over 157. So that's also passing. It's more than, or it's exceeding the limit of L over 150. So we are good. We move down right here and you can see the applied moment. That's the calculated applied moment. And this includes not just the regular lateral moment, but the moment that's induced by the P delta effects. So this is everything right here. And then this is your wall's capacity multiplied by the proper safety factor, which is 0.9 in this case. So 1.98. And it shows you here the location, it shows you the governing load combination. Same thing right here. Those are some of the checks that we have to do. This is the PU, the gravity load divided by AG. And this is important because that needs to be compared to 0.2 multiplied by F prime M for walls with an aspect ratio or with walls with the height to thickness ratio of less than 30. And of course, if it was more than 30, then this number becomes 0.05 multiplied by FM. Either way, we're good on this front and no issues there for us to worry about. Moving on to the serviceability check. This is saying that we have a max deflection of 1.2 inches and an L over 157. However, IBC 2024, just like many of the IBCs before it, they allow you to multiply wind load by 0.7 for serviceability. So if I can go to the combination tab and adjust that deflection combination instead of 1.0 wind, I can make it 0.7 wind, and we will get a much more favorable deflection results. As you can see here, I already did this and I changed it to the 0.7, and now you have an L over 224. So that's fantastic. And your actual max deflection is 0.85. So just kind of be careful as you use these things and as you interpret the results, just be careful how you go about them. And ENERCALC tries as much as we can to provide a lot of the stuff here in the summary without overwhelming the user, but at the same time providing key information that is needed to make decisions. Moving on to the reinforcing limit check. So ENERCALC calculates rho for the wall, which is this equation right here. And for us to be tension controlled, and ENERCALC only designs the walls oh, they have to be tension controlled for this module to work at this time. That's what we cover, and so that's why we make sure here we calculate row max for you, and we calculate the actual row. Actual row is again calculated by this right here. Row max, this equation is for fully grouted walls. This equation is for row max if the wall isn't fully grouted. And of course, these two equations right here for the strain, for the tension strain. And this is the equation changed from TMS 402, the 2016 to the 2022, yeah. So the equation changed. So whatever code here you're using in ENERCALC, it will follow the proper equation. But either way, it tells you here that the row max is 0.007, while actual row is 0.0025. You are well within the way under the row max, so you're good to go. And definitely, it's a tension controlled section. Lastly, here we have the reactions. So ENERCALC reports the max reactions for your convenience. It displays the horizontal reaction, vertical reaction, and again, the height to thickness ratio, slenderness ratio is displayed here as well for quick reference. You can click also, another thing worth highlighting is if you click on calculations and you go to the strength design, you will see a lot of intermediate values such as the cracked moment. You can see the PU here, the applied vertical load. You can see row max. You can see I cracked. You can see all kinds of important intermediate information here that would help you along the way. And I always tell people, make sure you take advantage of the 2D and the 3D dynamic sketches that ENERCALC offers. You can see all of your loads here. I isolated the vertical load, I isolated the lateral load. You can see this is for wind and this is for seismic. And you can see it in 3D here. You can play with it. And this is a full 2D sketch with some geometry and loads and everything. So this makes sure that you are depicting what you're trying, what's the intended construction assembly looks like. So this kind of concludes this part of the masonry portion, masonry slender wall portion of the presentation. Please, you can always go to for our users page here and make sure that you sign up for future office hours. It's a very simple process to sign up. And I want to let you guys know that ENERCALC team has been prioritizing FaceTime with all of our users across the country for a couple of years now, honestly. But we're increasing our presence in many national and local conferences. But the month of September is going to be really busy. We're going to be at SEOC in California. We're going to have Derek and Chelsea, two of our engineers there. I personally will be in North Carolina conference, the SEA of North Carolina. Seth is going to be later on or the same day actually, in the SEA of Ohio. And again, Derek and Chelsea at the end of the month will be at the Northwestern Conference States Conference right there. So you'll hopefully, if you live anywhere near us or if you're attending any of these conferences, please come and say hi and come and meet with us. So I want to remind everyone that you will receive an email with a PDF certificate within 10 days. And now we are open for Q&A.
All right, let's dive into some Q&A. First question, are there plans for adding a module for designing masonry opening jambs in walls, such as windows or doors? There are no plans at this time to add support for openings in the Masonry Slender Wall module. Again, we always want to remind everybody, if you have feature requests, if there's things that would be important to you that you'd like to see incorporated in the software, we always want to see those sent over to the support team, support@enercalc.com, just like Mac is showing here. That's how things climb the leaderboard to get attention from the development team. That's how the engineering team prioritizes, what features are the most important that we need to write technical specifications for and incorporate into the software. All right, next question. Can unreinforced walls be analyzed? Mac walked us through the process of assigning reinforcement conditions. The Masonry Slender Wall module is not designed to design plain unreinforced walls. Next question. Partially grouted means by length, correct? As in fully heighted, sorry, fully grouted, full height
Full
grouted
height
cells
grouted
of
cells.
48 inches on center. So typically in the context of masonry wall design, a wall is designated as either fully grouted or partially grouted. Fully grouted means you just fill it up solid. Partially grouted meaning only specific cells, the reinforced cells, would be grouted. And so that when you have a partially grouted wall, usually that grout is occurring at the same spacing as your reinforcement, only in select cells. Mac, go ahead if you want to add
No,
on
yeah,
that.
that's absolutely right. Yes, so it's in the terms of the wall by length. So yes, if you have reinforcement at 32 inch on center, then that cell where you have the reinforcement will be grouted. The other cells are empty, so that is a partially grouted wall. Unless you go out of your way and you leave no cell behind and you grout everything solid, then you are considered partially grouted.
Yeah, and so that's the
Yes.
exception to the rule of thumb that I just kind of made reference to. Mac touched on that early in the session. There are conditions under which you would reinforce only select cells, but grout every cell. Debris impact for tornado shelters would be one of those conditions. So it is true that you could have a fully grouted wall that has grouted cells that are not reinforced, but you would typically not have any condition where you have a reinforced cell that's not grouted. Hopefully that makes sense.
Yeah, and so yeah, sometimes gymnasiums they require that, and sometimes small I call them makeshift storm shelters. They're not exactly storm shelters, not FEMA rated, but they're still they want that additional protection. But I know for IC 500 FEMA rated storm shelters, as a requirement, you have to have everything fully grouted and you have to have, I think, number 5 bar minimum in every cell. But many people kind of, or at least here in Oklahoma, they like to do half and half where they fully grout it, but they still don't fully reinforce it. Either way, those are special conditions, and
Yeah,
they do occur every now and then for special requirements.
for sure. All right, next question. Does the design strip width ratio the reinforcing widths
Yes.
smaller than the bar spacing? Yes. So if you select a strip width, your reinforcing ratio is being adjusted accordingly.
Yes.
Good question. All right, next question. EC computes H over T based on nominal CMU width, not actual. In this example, H over T is 24 when it should be 25.2 for taller walls. This may be unconservative as you approach H over 2 of 30, excuse me, H over T of 30. Um, so this is something we definitely want to have the support team, the engineering team look at, and we'll reach out with more information on that. But that's
Yeah,
definitely a good
I
call out.
thought it was the well, yeah, the I have here this in front of me, the 9.3.4.4.2 from the TMS states that when the ratio of effective height to nominal thickness, so there the wording in there says nominal thickness, not actual thickness, and that is so. But yeah, send this question. We'll look into it. But I think it's nominal thickness, not actual thickness. Um, but we'll yeah, we can look into this more.
All right. Next question. Does ENERCALC through load combinations take the worst case of the eccentric load and windward or leeward load on the wall? Can you apply vertical wind uplift on the wall? Go ahead, Mac.
I'm trying to understand. It's so the way that the eccentric loading would work with the wind, they're additives. The equations are additives. So we're not trying to say is the wind helping you or is the wind going against you. We're not doing that. It's that the effect of P deltas are additive, and the equation actually straight up adds them together from the TMS.
Right. Okay.
So
Chris, if you
it
have more
wouldn't
questions
separate
on
that.
that, feel free to reach out to the
You
support
apply
team if you want to
vertical.
dig deeper on that one. Or if you want to ask a follow up, go ahead. We'll be here for a few
Yeah.
minutes. All right. Next question. I'm using version 20.25 July 9th. Seems like FR selection table tensile stress normal to the joint. Values for partially grouted hollow unit is missing. Can you please verify the latest version these values are added? Mac, are you familiar with the specific location this question is
Yes, that's
referencing?
nominal to joint values. He's talking about the one in ENERCALC. Yes, he's talking exactly about the one that I used, the one 84. So let me actually pull this up because I think this is worth looking into. Yeah, you can move on to the next question until I pull up
Sure.
ENERCALC here.
Next question. Can you use this slender wall calculation for basement walls retaining earth? So we do have, hopefully everybody's aware that we do have a series of modules that are specifically designed for earth retention capabilities. However, if you have I understand there may be conditions where you have a heavily loaded axial load condition where you're more worried about axial, but you also have lateral behavior in the mix. That might come down to a judgment situation where you need to kind of bracket your problem between the use of since you said it's a basement, use of the restrained top retaining wall module, and then also looking at the slender wall module because you should be able to draw your own loads that imitate the lateral effects of earth pressure, especially if you've already analyzed in the other modules. So um, if you have a heavily loaded, axially loaded wall where you're worried about slender wall behavior and you have additional effects from earth pressure, um, you may uh, you may want to look at both of those tools to address that issue.
Okay.
Go ahead, Mac.
Yeah, okay. Can you see me? You see the
Hmm.
screen, right? So he's talking about this part right here. And let me show you. This is the table I believe that he's referring to, that it's missing that middle piece. So we're showing here hollow units fully grouted. This is the reference table that ENERCALC includes. We show the hollow units fully grouted, but we don't show the hollow units ungrouted. And that's actually the value that I used in my example, which is the 84 right here. This is what he's referring to. That's not included. Yeah, please send us a feature request, and we'll make sure that this at least gets referenced in there, so you can easily grab it and use it.
All right, next question. Could you show how to check the out of plane? So a lot of what Mac did has to do with out of plane flexure, but Mac, do you want to just quickly highlight your output results on the right hand side when it comes to checking the out of plane
Yes.
results?
Okay. Right here. So you're talking about the moment check right here. This one, the MU, this is the applied moment. This applied moment, this number, the 1.126, is a combination. The equation in the TMS, it has two pieces. The first part, which is the regular moment that you get from wind or what seismic or whatever you have that's applied laterally. And then there's another component that gets added here that has to do with the vertical load that you applied and the delta effect, or the p little delta effect. So there's additional induced moment from that eccentric with the loading that has eccentricity. So that is right here is your applied moment. Then right here, this right here is your capacity. But again, the capacity has an involved equation that takes into effect the um, the the p little delta effect on the wall, and of course it takes into effect the slenderness ratio, which is um, the 30 to 1 that we were just talking about, and bring that up right here into this. But the equation is a little bit involved. I can try to pull them up here for you, but there is a process to it, and of course, if you're fully grouted and if you're not fully grouted, there's a flow chart for this. I'm not sure if I'm answering the question properly, but if you're trying to just find the quick numbers, this is your capacity and this is your applied load. But how we reach to this, that's an involved process that I can probably answer a little
Yeah,
time.
for sure. And the second question is similar. Can the masonry walls be designed out of plane? Can you just briefly revisit the slides for us where you showed where you were inputting out of plane loads to get the moment demand on the wall?
Yes. So if you so this is our wall right here, pin, and then you move on to the next piece, which is the loads. This is vertical, And because we have eccentricity here, this is gonna induce some moment on the wall. But then moving on, you have another tap right here next to vertical that says lateral. This tap takes the full wind load on the building or on your wall, and then it also takes the full seismic load that's induced by the wall weight, and it kind of uses both of them in the combinations as needed. And then right here, you can apply a concentrated point load that's lateral, and you can apply it at whatever height you want from 0 all the way to the top of the wall. So if it's at the middle of the wall, then you say it's 8 feet above the ground. If it's 3 feet above the ground, whatever you want. And then right here, that is the distributed uniform lateral load on the wall. That's in addition to the wind. You can say, I have additional lateral load at the bottom, maybe from 0 to 5 feet, or maybe from 0 to 8 feet. I want to design the wall for additional lateral load, or maybe not from 0 to 5, maybe from 3 to 8, or whatever you want. So you can add all of this. All of this is designing the walls for out of plane. Now, if your question was in plane, then that is a masonry shear wall. And we do have a different module for masonry shear walls. But if you're talking out of plane, just regular out of plane, then all of this feeds into your out of plane design for the wall. That's exactly what we've been doing with what we do with this module.
Yeah, exactly. And just while Mac has this slide up for us, a quick callback to our earlier question about the use of this module to look at basement walls, especially masonry basement walls where you have axial load and soil load. You could use your concentrated load and distributed lateral load tools here if you were interested in synthesizing some kind of an out of plane effect.
And the thing here to know is that the reason that I wouldn't recommend using this for basement wall
Yeah,
is
you
that
don't
if
have
you
your H soil pressure case here.
yeah, you wouldn't have that. You wouldn't be able to put triangular loads here. This is gonna be distributed all the way. So you're kind of like, just a uniformly distributed. So you're penalizing your wall. So that's why. But I guess yeah, you can do something here where you call it out single story. So pin at the top, pin at the bottom, and you can kind of do something. It's not necessarily designed for that, but you can do some voodoo there.
Yeah. All right, next question. How would 2 layers of reinforcement be implemented?
So if you do this right here, if you say that you see my screen
Mhm.
with ENERCALC, or do you see the
Yes.
software? Okay. So if you uncheck the center rebar, what happens that it asks you what you want your D distance is. You can keep it the same if the bars are exactly next to each other and they're horizontal, then they still maintain the same D. But if you put them in a way where that D is being reduced or something, or maybe you're using different sizes or whatever it is you want to do, you can say, hey, I have maybe 4 inches worth of D there, and that gets implemented right there. But just make sure that you're putting 2 rebar inside your cell, and you detail it properly to show that specific dimension. And what happens as far as the area of steel, it just gets multiplied by 2, because now you're having number 5 rebar at 32 inches on center, but you're putting 2 number 5 rebar. So every cell gets 2 multiplied by 0.31, which is the area of number 5 steel. And you go from there, and you want to make sure that you're not, of course, exceeding your row max. But yeah.
All right, next question. Wind load from LRFD to ASD was 0.6 and seismic was 0.7. Did wind change to 0.7? Can you hop back to your load combinations for us real quick?
So when I did the example, the first screenshot, this was actually 1. So when you have it at 1, it says just wind only, and it gives you right here. I have 2 bars. 1 second. Let me go back to make this right. Okay, you see this? This shows right here wind only. Where'd it go? Serviceability. Yeah, wind only shows you 1.22 inches and 157 L over 157. That's wind only, but
if you go to the load combinations and you find that load combination and you right click it and you change the factor from 1.0 to 0.7 and you click OK, then it recalculates and now it shows you here that the 0.7 wind is 0.85 and of course 0.85 inches and then L over 224. So yeah, this is something that you have to manually override in your combinations.
And you could also turn off the only combinations if you're not interested in seeing
Correct.
deflection results, for example, for dead only, roof
Yes,
live only, etc. You can always
that's
use your
correct.
run or don't run controls to disable those.
That's correct.
All right, next question. So the properties of the 12-inch strip takes into account the partially grouted CMU at 32 inches on center. Are these section properties noted in the output for verification? Basically, just does the printed report show the relationship between the unit strip used for analysis relative to the spacing of the reinforcement and grouting?
Sure, I can print a report and see what that looks like. If it's reports it. We can go to another question until I open this.
Sure. Next question. Is there a way to enter the software without entering the PCC code every time? Highly recommend you go ahead and reach out to the support team. You should not be having to enter your product control code every time you access the software. So
Yeah,
definitely
not.
encourage you to reach out to us about that so that that doesn't cause you any more trouble. Next question is a repeat about the FR table. I think we already addressed that one. Can you explain again how you applied the 0.7 wind for serviceability deflection? Okay, Mac just went over that. You have, just like in our other ENERCALC modules, you have full control of your load combinations and you can manually intervene to control those. Next question. Is there a relationship between the CMU wall design and the required footing to support it? This module does not get into structural effects going down to the footing. Some of the retaining wall modules and shear wall modules do look at more global stability, overturning in some cases soil bearing pressure as well. As far as I'm aware, this one does not. Mac, go ahead if you have thoughts on that.
No, I agree with you. What you're saying is absolutely right. Yeah, there isn't.
All right, next question. Or did you want to circle back to the printed report question, Mac?
Yeah, that's what I'm trying to do here.
Oh, sure. Okay. Well,
I
we'll go
have
with the next question while we wait. When using
yeah.
one number 5 8-inch rebar, fully grouted, sorry, one number 5 at 8 inches, fully grouted, reinforced in each cell, a message appears indicating that does not meet the reinforcement limit. How can I model this condition? So that's talking about a
one number
fully
5.
grouted, fully reinforced condition.
One number 5 to 8-inch rebar.
I think
Well,
one number 5 at 8, meaning one number 5 every cell.
Yeah. Rebar fully grouted. A message appears indicating that it does not meet the reinforcement limit. Maybe it exceeds row
Well,
max.
that's what I was going to say.
You
You may be actually exceeding the demand in the wall. That may not be talking about a minimum reinforcement limit at all.
Let's see here.
Because if you have a heavily loaded wall, it could be that fully grouted when the number 5 at each cell is not adequate. So we'd want to see more detail about what the warning is that you're seeing.
This right here, see that?
Yeah.
If I do 5 8-inch on center, I'm getting this reinforcing limit check. Actual row is 0.01 and max allowed row max 0.006. And this is what's happening here is that you're exceeding row max, meaning that you're going to get out of the tension controlled. And if you're getting out of tension controlled, then this is your phi factor is not even right anymore.
So that's a callback to the limitation that Mac mentioned earlier, which is this module only supports the tension controlled behavior. And so you're not violating an absolute limit for reinforcement, but you are getting out of the tension controlled range. That's the reason that you're seeing that notification.
I've pulled up the report here. And so what we have here, we have 5 at 32-inch on center. And this is to call back here to you. Wall is grouted at rebar cells only. And then if you go down here, all of the results, it says results reported for strip width 12 inches. And you can see here that
So that's your area of
the
steel
area of steel is
ratioed for the
adjusted.
size of the strip.
Yes, because
Yep.
if it's the size of the size of the strip and the spacing, of course, of the rebar, because the rebar is at 5 at 32 inches, number 5 at 32 inch on center, and then you're only using the 12 inches, so that's what you end up with
Yep.
instead of using the full 0.31 area of
Yep.
rebar number 5.
So,
Okay.
Chris, hopefully that answers your question. When you go down to the lower sections of the tabular outputs on your printed report, you'll be able to see how that reinforcement's actually spreading out with the relationship between the strip width and the spacing of the grouted cells, reinforced cells. All right. Well, Mac, we have cleared our queue. We're about 20 minutes after the hour here, about 18 minutes. Do you want to go ahead and close us out with any final thoughts and a teaser for next month?
Yes, that's an exciting part right here. So yes, for next month, we have our session on September 10th, and it's going to be the torsional analysis of rigid diaphragm module. This is very exciting. It's going to be a little bit of technical heavy session, but we're very excited to present this one.
All right, outstanding. Well, again, we thank everybody for taking the time to be here today. Our engineering team always looks forward to these sessions every month, all the great questions, all the great interaction with you guys. So we look forward to seeing everybody next month for another great session.